Before there were stars, before there were galaxies, before light learned how to travel across space, there was silence. Not the kind of silence we experience on Earth, but a deeper, more complete stillness. A universe without structure, without form, where matter and energy were evenly spread, and nothing yet had a name. Tonight, we are not rushing anywhere. There is no destination to reach, no revelation to chase. Instead, we will move slowly, patiently, through one of the most extreme and misunderstood phenomena in the universe: black holes. Not as monsters, not as cosmic vacuum cleaners, but as natural consequences of gravity, time, and mass, quiet endpoints in the long lives of stars. As you listen, there is nothing you need to remember, nothing you need to hold on to. These words are designed to drift past you the way starlight drifts across interstellar space. 1. The shape of space. To understand black holes, we need to begin somewhere calm, not with collapse, not with destruction, but with space itself. Space is not empty. Even where there are no stars, no planets, no visible matter at all, space still exists. It stretches, it bends, it responds to mass. A helpful way to imagine this is not as a void, but as a fabric, smooth, continuous, and flexible. When nothing rests upon it, this fabric lies flat. But when something with mass appears, a planet, a star, or a galaxy, the fabric curves gently around it. This curvature is what we experience as gravity. Objects are not being pulled in the traditional sense. Instead, they are following the natural curves of space itself. The heavier the object, the deeper the curve. Most of the time, these curves are subtle. Earth gently bends space, holding the moon in its orbit. The sun bends space more strongly, keeping the planets circling in quiet, predictable paths. But there are places in the universe where the bending becomes extreme, where space curves so deeply that the rules we rely on begin to soften. Black holes are born in those places. 2. Stars that refuse to stay still. Stars are not static objects. They are ongoing processes. At their cores, nuclear reactions push outward, a steady pressure created by atoms fusing together, releasing energy. At the same time, gravity pulls inward, trying to compress the star under its own weight. For most of a star's life, these two forces remain in balance. Outward pressure, inward gravity, a quiet agreement. This balance can last for billions of years, but nothing in the universe lasts forever. Eventually, a star begins to run out of fuel. When that happens, the outward pressure weakens. Gravity, patient and relentless, does not. For smaller stars, the collapse is gentle. They shrink into dense remnants, white dwarfs, quietly cooling over unimaginable spans of time. For larger stars, the ending is more dramatic. As gravity overwhelms the core, the star collapses rapidly, rebounds, and explodes outward in a supernova. For a brief moment, it can outshine an entire galaxy. But even then, gravity has not finished its work. What remains at the center of that explosion depends on how much mass the star once had. And for the most massive stars of all, there is only one possible outcome: collapse without limit. 3. When collapse has no bottom, imagine compressing Earth down to the size of a marble. Its gravity would become extreme. Now imagine compressing the sun down to the size of a city. its gravity would become overwhelming. A black hole forms when an enormous amount of mass is squeezed into an incredibly small volume, so small that the curvature of space becomes nearly vertical. At this point, nothing can resist gravity. Not atoms, not light, not time itself. This does not happen suddenly. There is no instant hole appearing in space. Instead, a region forms where escape becomes impossible. This boundary is called the event horizon. It is not a physical surface. There is nothing solid there, but it marks a line in space beyond which the future points inward. Once crossed, all paths lead deeper. 4. The quiet meaning of an event horizon. The event horizon is often described as the point of no return. But this phrase can feel dramatic. In reality, it is simply a boundary of information. From outside the horizon, events occurring beyond it can no longer send signals outward. Light cannot escape. Radio waves cannot escape. No message can cross back over. From far away, a black hole appears calm. It does not glow on its own. It does not announce itself. Only when matter falls toward it does the surrounding space begin to shine. Gas heats up. Dust accelerates. Radiation spills outward. But the black hole itself remains dark, silent, unmoving, and yet it shapes everything around it. Time begins to slow as you approach a black hole. Something unusual happens. Time changes. From your own perspective, everything feels normal. Your heartbeat remains steady. Your thoughts unfold as they always have. But to a distant observer, you appear to slow down. Your movements stretch. Your signals take longer to arrive. This is not an illusion. Time itself is responding to the curvature of space. The stronger the gravity, the slower time flows. Near the event horizon, this effect becomes extreme. To someone watching from far away, you would appear to freeze in place, never quite crossing the boundary. Your image would fade, redden, and dim, but never disappear. From your perspective, you would cross the horizon without noticing a precise moment. There is no alarm, no warning sound. Just a quiet continuation inward. 6. A universe that allows extremes. Black holes are not mistakes. They are not glitches or violations of cosmic order. They are permitted outcomes of the same laws that allow stars to shine and planets to form. Gravity does not stop working just because things become inconvenient. It continues patiently, even when matter can no longer support itself. In that sense, black holes are honest. They show us what happens when nothing is strong enough to push back. They reveal how space and time behave when stretched to their limits, and they do so without sound, without light, without urgency. Take a slow breath here. There is no rush. In the next part, we will drift closer toward the regions where matter spirals inward, where light bends into curves, and where time loses its familiar rhythm. For now, let your thoughts soften. You are safe. You are distant. And the universe continues quietly around you. There is a misconception that black holes are violent, that they tear through space, dragging everything inward with force and chaos. In reality, most black holes are remarkably quiet. From far away, they behave just like any other object with mass. If the sun were suddenly replaced by a black hole of equal mass, Earth would continue orbiting in almost exactly the same way. The darkness would be profound, but the gravity would feel familiar. This is because gravity does not depend on what an object is, only on how much mass it has and how concentrated that mass becomes. Black holes do not hunt. They do not reach outward. They wait. 1. Gravity as geometry. To understand why escape becomes impossible near a black hole, we need to gently reframe what gravity means. Gravity is not a pulling force acting across empty space. It is the shape of space itself. Mass tells space how to curve. Curved space tells matter how to move. Near everyday objects, this curvature is subtle. Paths bend slightly. Time slows by fractions of a fraction. But as mass becomes more concentrated, space bends more sharply. Near a black hole, the curvature becomes so extreme that every possible path forward leads inward, not because something is dragging you, but because the geometry allows no alternative. Trying to escape a black hole is like trying to walk north from the North Pole. No matter which direction you choose, you are still moving south. 2. Escape velocity and its limits. One way to describe black holes is through the idea of escape velocity. Escape velocity is the speed an object needs to permanently leave the gravitational influence of another object. For Earth, this speed is about 11 kilometers per second. For the Sun, it is much higher. As objects become more massive and compact, their escape velocity increases. At a certain point, the escape velocity exceeds the speed of light, and since nothing can travel faster than light, escape becomes impossible. This threshold defines the event horizon. Inside it, every possible future leads deeper inward. 3. Light that cannot leave. Light usually feels unstoppable. It crosses galaxies. It escapes stars. It carries information across billions of years. But light follows the shape of space. And near a black hole, space curves so deeply that light itself bends inward. Photons can orbit the black hole, circling in unstable paths. Some spiral inward, some briefly escape. But once light crosses the event horizon, there is no outward path remaining. This is why black holes are black. Not because they consume light aggressively, but because light cannot find a route back out. 4. The photon sphere just outside the event horizon exists a strange region called the photon sphere. Here, light can orbit the black hole in closed loops. If you could pause time and observe from a safe distance, you might see rings of light circling endlessly. This region marks the last place where photons can still hover before inevitability takes over. Even here, the balance is delicate. The smallest disturbance sends light either outward to freedom or inward to darkness. Nothing remains suspended forever. 5. Falling without falling. What does it feel like to fall toward a black hole? From far away, it feels ordinary. There is no sudden pull, no acceleration beyond what gravity already provides. As you drift closer, tidal forces begin to appear. Gravity pulls more strongly on your feet than on your head. This difference stretches objects along the direction of motion. Near small black holes, this stretching becomes extreme. The process has an informal name, spaghettification. But the word sounds more violent than the experience would feel. For much of the journey, there is no sharp boundary, only a gradual increase in the difference between near and far. 6. Different black holes, different experiences. Not all black holes are the same. Small black holes have intense tidal forces near the horizon. Large black holes, especially supermassive ones, are gentler at their edges. A supermassive black hole at the center of a galaxy can have an event horizon larger than the orbit of planets. You could cross that horizon without noticing anything unusual. The danger lies deeper inside. where gravity grows stronger with every passing moment. The size of the black hole determines how forgiving the approach can be. 7. The silence of infall. There is no sound in space. But even metaphorically, black holes are quiet. No explosion marks the crossing of the horizon. No flash announces arrival. To the falling observer, the universe ahead looks normal, at least for a while. Stars remain visible. Light continues to arrive. It is only the outside universe that begins to disappear. Signals from behind grow weaker. Time stretches. The universe seems to accelerate away. 8. Information and the edge of knowing. One of the deepest questions in physics concerns what happens to information that falls into a black hole. Information in physics is never supposed to be destroyed, yet black holes appear to hide it completely. From the outside, everything that falls in seems to be erased. Mass remains. Spin remains. Charge remains. But all other details vanish. This tension between gravity and quantum mechanics remains unresolved. As it approaches the event horizon, its motion appears to slow. Each second of its time takes longer to reach you. Light emitted later takes more time to escape. Eventually, the object seems to freeze, hovering just above the horizon. Its image fades, reddens, and dissolves into darkness. From your vantage point, it never quite crosses. 4. Crossing without knowing, but for the falling object, time continues normally. There is no sudden pause, no sensation of slowing. The event horizon is not marked by a wall or signal. It is simply a location in space where future paths narrow inward. Crossing it feels no different than drifting through any other region. This difference in perspectives is one of the strangest features of black holes. Two observers, both correct, experiencing entirely different realities. 5. Time and distance exchange roles inside the event horizon. Space and time begin to trade roles. Moving forward in time becomes equivalent to moving inward in space. Just as you cannot stop time from advancing, you cannot stop the inward journey. This is not because of force, but because of structure. The geometry of space-time leaves no alternative. 6. The narrowing of possibilities. As one moves deeper, the number of possible futures decreases. Outside the horizon, you can choose directions. Inside, every possible path leads toward the center. This does not happen abruptly. It is gradual, inevitable, and silent. 7. The center, that is not a place. At the heart of a black hole lies what physics calls a singularity. This is not necessarily a point in space as we imagine points. It is a region where our equations fail. Density becomes infinite. Curvature becomes infinite. These infinities do not mean reality is truly infinite. They mean our descriptions have reached their limits. The singularity is not understood. It is a placeholder for future knowledge. 8. Time's final compression. As one approaches the singularity, tidal forces increase. Differences in gravity across small distances become extreme. Objects are stretched, compressed, and eventually torn apart. But again, this depends on the black hole. In massive black holes, these forces remain gentle until very deep inside. The universe allows many gradients of experience. 9. The outside world accelerates away from the inside perspective. The universe outside appears to speed up. Light from distant stars arrives rapidly. Cosmic history unfolds quickly. billions of years can pass in moments from the falling frame. This is not cinematic exaggeration. It is a consequence of time's uneven flow. 10. Resting with elastic time. For now, you do not need to picture these extremes. Let time return to its familiar pace. Your breathing is steady. Your surroundings are calm. Black holes remind us that time is not rigid. It bends, stretches, and flows differently depending on where you are. This flexibility does not threaten us. It simply exists. In the next part, we will explore the regions around black holes where matter gathers, heats, and slowly spirals inward. For now, allow time to settle. There is no rush. Black holes are dark, but the space around them is often filled with light. This light does not come from the black hole itself. It comes from matter that has not yet crossed the edge. 1. Matter does not fall straight in. When gas or dust approaches a black hole, it rarely falls directly inward. Instead, it begins to orbit. Just as planets orbit stars, matter circles the black hole along curved paths. As it does, it slowly loses energy. Friction, collisions, magnetic interactions. No, these forces cause matter to spiral inward in wide, graceful arcs. This structure is called an accretion disk. 2. The quiet violence of accretion disks can become extremely hot. As particles rub against each other, their energy increases. Temperatures rise to millions of degrees. At these temperatures, matter glows. X-rays spill outward. Radiation escapes into space. Ironically, some of the brightest objects in the universe are powered by black holes. The darkness at the center creates brilliance around it. 3. Order emerging from motion. Despite their energy, accretion disks are not chaotic. They follow patterns. Angular momentum is conserved. Material flattens into a disk. The inner regions orbit faster. The outer regions move more slowly. This creates sheer layers sliding past one another. Over time, energy is radiated away, allowing matter to sink deeper. This process can take thousands or millions of years. Nothing rushes. 4. Jets that point away. In some black holes, not all matter falls inward. Under certain conditions, powerful jets form. These jets shoot outward from the poles of the black hole at near light speed. They can extend for thousands of light years. These jets are not emitted by the black hole itself, but by the magnetic fields of the accretion disk. The black hole shapes them indirectly. Even here, the black hole remains silent. 5. Feeding the giants at the centers of galaxies lie supermassive black holes, millions to billions of times the mass of the Sun. When they actively feed, their accretion disks can outshine the galaxy itself. These systems are called active galactic nuclei. From across the universe, we can see their glow. Not the hole, but the slow meal surrounding it. 6. A delicate balance. Most black holes are not actively feeding. They sit quietly, barely interacting with their surroundings. Accretion requires supply. Without nearby gas or dust, a black hole can remain dormant for billions of years. It does not demand matter. It accepts what drifts close. 7. The last stable orbit near the event horizon exists a boundary called the innermost stable orbit. Inside this radius, orbits become unstable. Matter can no longer circle safely. It begins a final inward plunge. This transition is smooth. No alarm sounds. The disk simply ends. 8. Light on the edge. The light we observe from near a black hole is distorted. Gravitational lensing bends it. Time dilation reddens it. Photons climb out against gravity, losing energy as they go. What reaches us is stretched and softened. Even brightness becomes tired. 9. Calm. Within extremes, though the physics is intense, the motion is gradual. Spirals widen. Heat builds slowly. Nothing snaps or jerks. The universe prefers continuity. Even near black holes, change unfolds patiently. 10. Letting the spiral fade, you do not need to follow the inward path. You are only observing from a distance. The spirals can slow in your mind. The light can dim. There is no need to stay near the edge. In the next part, we will explore how black holes grow, merge, and quietly reshape galaxies over cosmic time. For now, rest with the image of slow rotation and gentle light. Black holes are often imagined as sudden, catastrophic objects, but most of their existence is defined by patience. They grow slowly. 1. Growth is not guaranteed. A black hole does not automatically become larger. It only grows when matter comes close enough to be captured. In much of the universe, space is sparse. Stars are far apart. Gas is thin. Dust drifts quietly. A black hole placed in an empty region may remain unchanged for billions of years. It does not seek. It waits. 2. Feeding in small amounts. When matter does fall in, it often arrives in fragments. A thin stream of gas. A passing cloud. Occasionally, a star that wanders too close. Most of this material never reaches the center. It heats, glows, and radiates energy away before crossing the horizon. Only a portion adds to the black hole's mass. Growth is inefficient. 3. Stellar encounters. When a star approaches too closely, tidal forces stretch it apart. This is called a tidal disruption event. The star is pulled into a long stream. Some material escapes. Some spirals inward. From far away, we can see a temporary flare of light. Then the system returns to quiet. These events are rare. Galaxies are large. Precise encounters are uncommon. 4. Mergers in silent black holes can also grow by merging with one another. When galaxies collide, their central black holes begin a slow dance. They orbit each other for millions of years. Gradually, they lose energy. Eventually, they merge. This process releases ripples in spacetime called gravitational waves. These waves pass through the universe without sound, without light. They stretch space itself by tiny amounts. We can now detect them, not by seeing, but by listening to spacetime's rhythm. 5. Growth on cosmic timescales. Supermassive black holes did not appear overnight. They formed gradually through countless small events. Accretion, mergers, quiet accumulation. Their growth mirrors the growth of galaxies themselves. Slow, layered, non-linear. Nothing here is rushed. 6. Black holes and galactic order. Despite their reputation, black holes can stabilize galaxies. Their energy output can regulate star formation. Too much gas, jets and radiation heat it. Too little, gas cools and collapses. This feedback helps galaxies maintain balance. The black hole does not dominate. It participates. 7. A central stillness. At the heart of many galaxies, the central black hole remains mostly inactive. Our own galaxy's black hole is quiet. It emits little energy. It consumes little matter, yet its presence shapes the galaxy's core. Gravity does not need to act loudly to be influential. 8. The long wait between events, between feeding episodes, nothing happens. No light, no motion worth noting. Time passes. Stars orbit, dust drifts. Space remains calm. This long inactivity defines most black holes' lives. They are not constant engines. They are intervals. 9. Letting growth become abstract. You do not need to picture the details. You do not need to follow individual particles. The important idea is slowness. Accumulation without urgency. Change without drama. The universe allows vast transformations to occur quietly. 10. Settling into the scale growth measured in millions of years does not demand attention. It can fade into the background. Let the idea of time stretch. Nothing is pressing forward. In the next part, we will step back and observe black holes from a wider perspective. How we detect them without ever seeing them directly. For now, rest in the idea that even the most extreme objects spend most of their existence doing almost nothing. Black holes cannot be seen directly. They emit no light of their own. They reflect nothing. And yet, we know they exist, not through images, but through influence. 1. Gravity leaves traces. Even when something is invisible, its gravity remains detectable. Stars orbit unseen companions. Gas clouds accelerate unexpectedly. Light bends where nothing appears to be. These clues accumulate. They point to mass where no luminous object can be found. This is how black holes first revealed themselves, not as objects, but as absences with weight. 2. Stars that orbit nothing in some systems. A visible star orbits an unseen partner. The orbit reveals mass. The mass exceeds what a normal star could be. No light is emitted. No surface is observed. Only gravity remains. This invisible partner fits every prediction of a black hole. 3. Motion at galactic centers. At the centers of galaxies, stars move rapidly. They follow tight, fast orbits around an unseen point. By measuring these motions, astronomers calculate mass. In many galaxies, the mass is enormous, millions or billions of times that of the Sun, and it occupies a very small region. Nothing else explains this but a supermassive black hole. 4. Light that bends around emptiness. Gravity bends light. When light passes near massive objects, its path curves. This effect is called gravitational lensing. In some cases, we see light arcs or rings around regions of darkness. The light reveals the mass without revealing the object. The lens points to something present but unseen. 5. Hearing the universe. The most recent confirmation came not from sight, but from vibration. When black holes merge, they disturb space-time itself. This disturbance travels outward as a wave, not a sound wave, a gravitational wave. Sensitive instruments on Earth can detect these ripples as tiny stretches and compressions of space. They arrive quietly, having traveled billions of years. The universe announces events without light. 6. Patterns in the noise gravitational wave signals have structure. They rise in frequency, they peak, they fade. From these patterns, scientists infer mass, spin, and distance. No image is needed. The shape of the wave contains the story. 7. Shadows, not objects. Recently, we have captured images of black hole shadows. Not the black hole itself, but the silhouette it creates against glowing matter. A dark circle surrounded by light. This is not a photograph in the traditional sense. It is a reconstruction from many observations, a confirmation, not a discovery. 8. The comfort of indirect knowledge. Much of science works this way. We infer. We model. We compare predictions with observation. Black holes fit remarkably well. Their behavior matches equations. Their influence matches expectation. They are extreme but consistent. 9. Absence as evidence. Black holes remind us that absence can be meaningful. Silence can carry information. The universe does not require everything to be visible to be understood. Some truths are felt indirectly. 10. Resting with the unseen. As you listen, you do not need images. You do not need shapes. Let the idea of gravity stand alone, an influence that persists even when nothing is seen. The unseen does not demand attention. It simply exists. In the next part, we will explore different kinds of black holes, from small remnants to cosmic giants. For now, let the invisible remain gentle. Not all black holes are the same. They differ in size, in origin, and in the role they play within the universe. What unites them is gravity. What distinguishes them is scale. 1. Stellar mass black holes. The most common black holes are formed from collapsing stars. These are called stellar mass black holes. They typically contain between 3 and several dozen times the mass of the Sun. They are born in violence, supernova explosions, but live quietly. Afterward, many drift through galaxies, almost unnoticed. Unless something wanders too close, they remain invisible. 2. Binary systems. Some stellar mass black holes exist in pairs with stars. In these systems, the black hole slowly draws material from its companion. Gas streams across space, forming an accretion disk. Light appears. X-rays escape. These systems were among the first places where black holes were suspected. Not seen, but inferred. 3. Intermediate mass black holes. Between stellar and supermassive lies a quieter category. Intermediate mass black holes. Hundreds to thousands of solar masses. They are harder to find. Less dramatic. They may form from the merger of smaller black holes or the collapse of dense star clusters. Their existence fills a gap in our understanding of growth. They suggest continuity, not leaps. 4. Supermassive black holes. At the centers of most galaxies reside supermassive black holes. Millions to billions of solar masses. They did not form from single stars. Their origins are still debated. They may have grown from smaller seeds, fed steadily over time, or they may have formed directly from massive gas clouds in the early universe. Whatever their origin, they are ancient. They have shaped galaxies for billions of years. 5. The calm at galactic hearts. Despite their mass, supermassive black holes are often inactive. They emit little energy. They consume little matter. They sit at the center, anchoring orbits through gravity alone. Their influence is subtle but persistent. 6. Hypothetical black holes physics allows the possibility of black holes smaller than stars. Primordial black holes may have formed shortly after the Big Bang. They would be tiny, possibly microscopic, yet massive for their size. Their existence is unconfirmed. They remain speculative. But they remind us that black holes are not limited to one scale. 7. Spin and rotation. Black holes can rotate. Some spin slowly, others spin rapidly. This rotation affects the surrounding spacetime. It drags space itself around the black hole. This effect is called frame dragging. It changes how matter orbits, how jets form, and how energy is extracted. Rotation adds character without adding noise. 8. Charge and simplicity. Black holes can also carry charge, though most are likely neutral. Remarkably, black holes are defined by very few properties: mass, spin, charge. Everything else disappears behind the horizon. This simplicity is profound. Complex origins collapse into minimal description. 9. Diversity without personality. Though black holes differ, they are not individuals. They have no memory, no preference. They are outcomes, not actors. This neutrality makes them useful. Predictable, consistent. 10. Letting categories fade you. Do not need to remember the classifications. They are scaffolding, not destination. What matters is that black holes exist across scales, from the remnants of stars to the hearts of galaxies. Quiet, persistent, unchanging. In the next part, we will step further outward and see how black holes fit into the broader history of the universe itself. For now, let the idea of scale soften. Black holes do not exist in isolation. They are woven into the long history of the universe. From the earliest moments after the beginning of time to the slow evolution of galaxies, their presence has been quiet but enduring. 1. The early universe. In the first few 100 million years after the universe began, matter was simpler. There were no planets, no complex structures, only gas, mostly hydrogen and helium, slowly cooling and clumping together. Gravity worked patiently. Where matter gathered, the first stars ignited. Some of these early stars were enormous, far larger than stars formed today. When they ended their lives, they likely collapsed directly into black holes. These may have been the earliest seeds. 2. Seeds that would grow. Once formed, these early black holes began to shape their surroundings. Gas fell inward, energy spilled outward. Over time, they grew. Not rapidly, but steadily. These seeds may explain how supermassive black holes appeared so early in cosmic history. They did not arrive suddenly. They accumulated. 3. Galaxies take shape. As galaxies formed, black holes settled into their centers. Gravity naturally draws mass inward. Stars orbit, gas flows. Momentum redistributes. Over billions of years, this process repeated. Galaxies grew, black holes grew. Their histories became intertwined. 4. Feedback and balance. When black holes feed actively, they influence star formation. Energy released can heat surrounding gas. Hot gas resists collapse. This can slow the birth of new stars. At other times, cooling allows stars to form again. This cycle creates balance, not perfect balance, but enough to shape galaxies into recognizable forms. 5. Order without design. There is no plan, no blueprint. The patterns we see emerge naturally from simple rules. Gravity pulls, energy radiates, matter responds. Black holes follow the same rules as everything else. They are not exceptions. They are participants. 6. A long view of time, most of a black hole's influence is spread across vast spans of time, millions of years, billions of years. From this perspective, individual events lose importance. Only trends remain. Slow accumulation, gradual change. The universe is shaped more by patience than by drama. 7. Our place in the timeline. Human history occupies a narrow slice. All of civilization fits into a fraction of a cosmic second. Black holes existed long before Earth formed. They will exist long after the sun fades. This is not threatening. It is grounding. 8. Memory. Written in orbits. The influence of black holes can be read in the motion of stars, in the shape of galaxies, in the distribution of matter across space. They leave no marks on their own surfaces. They write history through gravity. 9. Letting history become distant. You do not need to follow the timeline. Dates are unnecessary. What matters is continuity. A universe unfolding slowly, with black holes as steady anchors. 10. Resting in deep time as you listen. Allow time to stretch. Let billions of years blur into a single calm idea. Nothing urgent happens here. History flows quietly. In the next part, we will explore what happens at the edges of our understanding, where black holes meet the limits of physics itself. For now, rest with the sense of deep, unhurried time. Black holes are not only objects in space, they are boundaries in understanding. They sit where familiar laws begin to soften, and where certainty gives way to careful questions. 1. Where physics meets itself. Two great frameworks describe our universe. One explains the very large, gravity, motion, the structure of spacetime. The other explains the very small, particles, probabilities, quantum behavior. Both work extraordinarily well in their own domains. But inside black holes, they meet, and they do not yet agree. 2. General relativity's prediction. According to gravity's equations, a black hole contains a singularity, a region where density and curvature become infinite. This is not a place where physics predicts something strange. It is a place where physics stops predicting anything at all. Infinity is not a result. It is a signal that our description is incomplete. 3. Quantum questions. Quantum theory resists infinities. It describes reality as discrete, uncertain, and probabilistic. When quantum ideas are applied near a black hole's core, they suggest new possibilities. Perhaps the singularity is avoided. Perhaps space becomes granular. Perhaps time behaves differently. These are not answers. They are directions. 4. The information puzzle. One of the most persistent questions is the fate of information. When matter falls into a black hole, its detailed structure disappears from view. From the outside, only mass, spin, and charge remain. But quantum theory insists that information cannot be destroyed. This tension is unresolved. It has motivated decades of careful thought. 5. Hawking radiation black holes are not perfectly eternal. At their edges, quantum effects allow a slow leakage of energy. This process is called Hawking radiation. It is extremely weak. For stellar mass black holes, it would take longer than the current age of the universe to notice any change. But, in principle, black holes can evaporate very slowly. 6. Evaporation and endings. If a black hole evaporates completely, what happens to the information that once fell inside? Does it return? encoded in radiation? Is it lost forever? Or is our understanding incomplete? These questions remain open. They do not disturb the calm. They simply exist. 7. Thought experiments as tools. Much of black hole research uses thought experiments. Carefully imagined scenarios tested against mathematical consistency. These exercises are not idle. They sharpen understanding. They reveal contradictions. They guide new theories. Progress is slow, but deliberate. 8. Acceptance of uncertainty. There is comfort in admitting uncertainty. Black holes remind us that knowledge is layered. Some layers are solid. Some are still forming. Not knowing everything does not diminish understanding. It completes it. 9. The edge is a place of rest. The edge of knowledge is not a cliff. It is a shoreline. Beyond it lies unknown water. There is no need to cross it tonight. You can remain here, observing quietly. 10. Letting questions settle you do not need answers to rest. Questions can remain open without demanding resolution. They can drift, unresolved, and still feel complete. In the next part, we will step away from equations and puzzles and return to the quiet experience of distance and scale. For now, allow uncertainty to soften. There is safety in distance. Black holes feel unsettling only when imagined up close. From afar, they are quiet features of a vast landscape. 1. Scale restores calm. The universe is large, enormously large. Between stars lie light years of space. Between galaxies lie millions of light years more. Black holes occupy tiny regions within this immensity. Their influence fades with distance. Beyond a certain point, their gravity becomes indistinguishable from that of any other object. 2. Rare encounters despite their reputation. Black holes are unlikely to affect everyday life. The nearest known black hole is thousands of light years away. Its gravity does not reach us. Earth's motion remains unchanged. The sun's path is steady. The universe is not crowded with danger. It is spacious. 3. Orbits that remain stable. Stars orbit black holes the way planets orbit stars, predictably, smoothly. Most orbits remain stable for billions of years. Chaos is not the norm. Order persists. 4. Perspective and fear. Fear often comes from scale confusion. When we imagine black holes at human distances, they feel overwhelming. When we place them where they truly belong, across cosmic distances, they become abstract. Their power is real, but remote. 5. The universe is mostly empty. Most of the universe is nearly empty space. Particles are sparse. Interactions are rare. This emptiness is calming. It means that extreme events do not crowd one another. They are isolated. 6. Stillness between structures, between galaxies. There is little motion. No collisions, no explosions, just slow expansion. Black holes exist within this stillness without disturbing it. 7. Knowing without proximity, we can study black holes without approaching them. Equations describe them. Signals reveal them. Distance does not reduce understanding. It preserves safety. 8. Letting the mind step back, you do not need to imagine falling. You do not need to imagine crossing thresholds. Step back. Let distance reassert itself. 9. Calm through scale. When objects are placed in their true proportions, they lose urgency. Black holes are powerful but small. The universe is gentle because it is vast. 10. Resting with perspective. As you listen, allow the scale of space to create calm. Nothing nearby is changing, nothing distant needs attention. Everything is where it belongs. In the next part, we will explore how black holes slowly change as the universe ages. For now, rest in distance. Nothing in the universe remains unchanged. Even black holes, which feel permanent, are part of a slow evolution. Their changes are subtle, spread across spans of time so large they are difficult to imagine. 1. Time on cosmic scales. When we speak of aging in space, we do not mean years or centuries. We mean millions, billions, and trillions of years. On these scales, even dramatic events become brief. Black holes persist, but they do not stand still. 2. The long pause between meals. For most of their existence, black holes do very little. They orbit quietly within galaxies. They drift with star systems. They wait. Feeding events are rare. Between them lie immense intervals of stillness. This inactivity defines their lives far more than growth. 3. Slow loss through radiation. At the very edges of black holes, quantum effects allow a faint leakage of energy. This process is unimaginably slow. A black hole the mass of the sun would take far longer than the current age of the universe to noticeably shrink. For supermassive black holes, the timescale is even greater. They are, for practical purposes, stable. 4. Cooling with the cosmos. As the universe expands, it cools. Energy spreads out. Temperatures drop. Over trillions of years, fewer stars will form. Galaxies will grow quiet. Black holes will find less and less matter nearby. Their growth will slow even further. 5. The era of darkness in the far future. Stars will fade. White dwarfs will cool. Neutron stars will darken. Black holes will remain among the last massive objects. Not active. Not luminous. Simply present. They will orbit silently through a dim universe. 6. The ultimate longevity? Because black holes evaporate so slowly, they may outlast everything else. They will persist long after galaxies lose structure, long after starlight ends. They are not eternal, but they are patient. 7. Change without witnesses. Much of this future will unfold without observers. No eyes to watch, no instruments to measure. Events will still occur. Time will still pass. The universe does not require attention to continue. 8. The calm of predictability. The physics of black hole aging is simple. No sudden transformations. No surprises. Just slow, steady change governed by known principles. This predictability is comforting. 9. Letting the far future blur. You do not need to imagine trillions of years. The details can fade. What matters is the sense of slowness. A universe that changes without urgency. 10. Resting with deep time as you listen. Allow time to stretch outward. Let beginnings and endings lose sharpness. Black holes age quietly. So does the universe itself. In the next part, we will explore what remains constant, even as everything changes. For now, rest in the idea that time moves gently when viewed from far enough away. There are discoveries that arrive with a bright image. A planet revealed in a telescope. A nebula painted across a screen. a galaxy captured as a soft spiral of light, but black holes demanded a different kind of attention. For most of human history, we had no reason to believe such objects existed, not because the idea was impossible, but because the universe did not offer them up easily. A black hole gives no comforting glow, no crisp outline. It hides its interior completely, and it reveals itself only through what it changes around it. And so, for a long time, black holes were not found in the way mountains are found. They were inferred quietly, through careful measurements, through small mismatches between expectation and reality. A star that should not be moving that fast, a system that should not be stable, but is. A region that should be empty, but has far too much mass. When you look at it this way, the story of black holes becomes gentle. Not a story of violence, but a story of patience, a slow refinement of the human ability to notice what cannot be seen. NASA describes the event horizon as a boundary beyond which the escape speed exceeds the speed of light, which is why even light cannot get back out. This isn't just a dramatic statement. It's a definition that tells you something about how knowledge works in the universe. There are places where information simply cannot return. And yet, even with that limitation, we have learned to listen, not to sound. Space carries almost no sound at all, but to subtler things, to motion, to bending light, to ripples in the geometry of spacetime. A black hole doesn't need to show itself directly for the universe to testify that it is there. For a long time, one of the clearest hints came from movement. In orbiting systems, gravity leaves fingerprints. When one object circles another, the details of that orbit reveal the mass at the center. If you can measure the speed, the shape, the period, the distance, you can infer what is being orbited, even if the central object is dark. This is one of the calm truths of astronomy. You can learn a great deal without ever seeing the thing itself. And it's fitting that black holes were approached this way first, because gravity is what they are most faithful to. Gravity is their signature. As observations improved, the story expanded beyond single star systems and into galactic centers. In many galaxies, stars near the middle move in tight, rapid orbits, as if drawn around an invisible anchor. When that hidden mass is calculated, it turns out to be enormous, concentrated into a region too small to be explained by clusters of ordinary stars. A supermassive black hole becomes the simplest explanation, not because it is a convenient idea, but because it matches how gravity behaves when mass becomes extreme. A boundary forms, an event horizon, a region where future paths tilt inward. That phrase can sound heavy, but it can also sound peaceful if you let it. Paths tilting inward is not a cosmic scream. It is geometry. And then, in recent years, something changed. We began to get images, not of black holes themselves, but of the shadows they cast. The Event Horizon Telescope is not a single instrument. It is a network of telescopes spread across Earth, working together like one planet-sized observatory. When it produced the first widely publicized image of a black hole shadow in the galaxy Messier 87, it showed a bright ring and a dark center, light bending around an invisible boundary, and a shadow formed by photon capture and gravitational distortion. That ring wasn't a painted symbol. It was evidence, a soft glow created by heated matter and a darkness created by gravity so strong that light could not take a clean path outward. It was the closest thing we could get to seeing a black hole, while still respecting the fact that black holes do not reveal their interiors. An image of absence. A gentle circle where the universe refuses to give you a direct view. But even that was not the most intimate way we learned to detect them. Because another kind of evidence arrived without light at all. Gravitational waves. These are ripples in spacetime. Disturbances produced when massive objects accelerate, especially when they orbit and merge. The first direct detection was made on September 14, 2015, observed by the twin LIGO detectors in Louisiana and Washington. What makes this so calming, in a strange way, is the scale. Those waves traveled across the universe, carrying a story from a distant merger. They passed through space for an immense length of time. Then, they reached Earth. And only then did the instruments notice a whisper, an almost impossibly small change in distance. The kind of change that seems too tiny to matter, and yet it mattered enough to confirm a new way of observing the universe. This was black hole evidence that did not require a picture, just a waveform, a rise and fall. A brief signal that said two dark objects spiral together, merged, and released energy as space-time itself trembled. It is hard to imagine something more quiet than that. A universe that can announce catastrophe through a signal that lasts less than a second and arrives as a gentle ripple. Now, there's another subtle truth that belongs here, and it's worth letting it settle slowly. Black holes are not just endpoints of collapse. They are also laboratories for physics. They sit at the meeting point of gravity and quantum behavior. They force us to ask questions we cannot avoid. One of those questions involves what is called Hawking radiation. The idea, in simplified form, is that quantum effects near the event horizon allow black holes to emit a faint thermal radiation, meaning they can lose mass extremely slowly over inconceivably long timescales. For a black hole with about the mass of the Sun, the predicted evaporation time is vastly larger than the current age of the universe. Numbers so large, they stop feeling like clocks and start feeling like pure abstraction. This is important not because we are trying to frighten ourselves with huge numbers, but because it reframes black holes as not perfectly eternal. They are patient, but not infinite. They are slow, but not frozen. And when you combine that with the information puzzle, what happens to the detailed information of what falls in? You begin to see why black holes are not only astrophysical objects, but also conceptual edges. NASA's description emphasizes that nothing about what happens within can reach an outside observer, which is exactly why these questions feel so sealed. The universe creates a boundary and then challenges us to understand what a boundary means. If you let your mind drift, you can hold on to one simple idea. We have learned to detect black holes in multiple ways: through the motion of nearby stars, through heated matter spiraling in accretion disks, emitting high-energy light as it loses angular momentum and energy, through ring-shaped shadows where light bends and disappears, and through gravitational waves, space-time itself carrying a record of distant mergers. The universe speaks in more than one language, and black holes forced us to learn languages beyond sight. Take a slow breath here. Nothing in this story demands urgency. Even the most extreme events become gentle when you place them at their true distance, at their true scale. In the next part, we will move closer to the lived environment around black holes, the way gas behaves, the way disks form and change, and how rotation can drag space-time into subtle motion, not with drama, just with patient detail. When matter approaches a black hole, it does not rush. This is one of the most misunderstood aspects of these objects. From a distance, it can look dramatic: bright light, hot gas, swirling motion. But up close, from the perspective of the matter itself, everything happens gradually. Matter does not fall straight inward like water down a drain. It circles. it hesitates. It takes long, curving paths through warped space. Gas in space almost always has motion. Even the thinnest cloud drifts with momentum inherited from ancient events. The collapse of stars, the merging of galaxies, the slow rotation of cosmic structures. When this gas encounters a black hole, that motion does not disappear. Instead, it becomes organized. The result is a rotating structure known as an accretion disk. An accretion disk is not solid. It is not smooth. It is a layered flow of particles, plasma, and magnetic fields, each element moving at slightly different speeds. The outer regions move slowly. The inner regions move faster. This difference in speed creates friction. Not friction like rubbing hands together, but friction on a cosmic scale, particles colliding, exchanging energy, heating gradually. This heating is what makes accretion disks shine. Not the black hole, the matter around it. Temperatures in these disks can reach millions of degrees. At such temperatures, atoms cannot remain intact. Electrons separate from nuclei. Matter becomes plasma, a state that responds strongly to magnetic fields. Those magnetic fields twist and stretch as the disk rotates. They act like invisible scaffolding, channeling energy and motion. This is where some of the most subtle behavior appears. In certain configurations, magnetic fields can redirect energy away from the disk itself. Instead of falling inward, some material is accelerated outward along the black hole's rotational axis. This produces jets, long, narrow streams of particles moving at speeds close to the speed of light. These jets do not come from inside the black hole. They originate from the disk and the region just outside the event horizon. The black hole shapes them indirectly by distorting space-time and dragging magnetic fields into alignment. Jets can extend thousands, sometimes millions, of light years into space. They pierce the surrounding galaxy, depositing energy far from their origin. Yet even these jets are not constant. They flicker, they weaken, they strengthen again. Like everything else near a black hole, they respond to supply. When there is little matter, there is little activity. There is a quiet lesson here. Black holes are not engines that run continuously. They are conditional. They depend on their environment. A black hole in a sparse region of space is almost indistinguishable from empty darkness. Only when matter arrives does the surrounding space become luminous. And even then, the black hole itself remains unseen. Closer to the event horizon, motion becomes more constrained. There exists a boundary known as the innermost stable orbit. Beyond this distance, circular motion is no longer possible. Matter cannot maintain a steady path. It begins a final inward journey. This is not a plunge. It is a transition. The disk simply ends. From that point on, the future points inward. Light emitted from these regions is distorted. Gravity stretches wavelengths, shifting colors toward red. Paths curve. Some photons escape. Others are captured. The closer the light is produced to the event horizon, the more altered it becomes. What reaches distant observers is already aged, already softened. If you imagine watching from very far away, you would see the disk slow. Time dilation stretches the motion. Events near the black hole appear to unfold more slowly than events far from it. This creates a strange visual effect, a region where time seems thicker, more resistant to change. But from within the disk, everything feels normal. Particles collide, energy transfers, motion continues. Perspective shapes experience. Accretion disks are not permanent. They can thin out. They can dissipate. When supply ends, light fades. The black hole returns to quiet darkness. No afterglow, no residual heat, just gravity. This rhythm, activity followed by long silence, defines the life of most black holes. They are not always dramatic. They are episodic, brief moments of visibility separated by immense spans of stillness. As you rest with this idea, there is no need to imagine heat or speed. Let the motion slow. Let the disk widen. Let the light dim. The universe does not rush matter toward its ends. It allows time. In the next part, we will explore rotation more deeply. How spinning black holes reshape space itself, and how motion can be transferred without direct contact. For now, rest with the image of matter moving carefully, step by step, through curved space. Some black holes are still, others rotate. This rotation is not decorative. It is structural. When a black hole spins, it does not simply rotate within space. It causes space itself to rotate with it. This effect is subtle at first, but near the black hole, it becomes unavoidable. Rotation is a consequence of origin. Stars spin, gas clouds rotate, galaxies turn slowly over billions of years. When a star collapses into a black hole, it does not lose this motion. Instead, the rotation becomes concentrated, compressed into a much smaller region. The result is a rotating black hole, often called a Kerr black hole. To understand what rotation means here, it helps to let go of ordinary intuition. A spinning black hole does not have a surface. There is nothing solid turning. Instead, space-time itself is dragged along. This phenomenon is called frame dragging. Near the black hole, space cannot remain still. Even objects that try to hover are forced to move, not because of wind, not because of friction, but because space-time itself is being carried around. There is a region around a rotating black hole where this effect becomes extreme. It is called the ergosphere. Within this region, it is impossible to remain stationary relative to distant space. Everything is compelled to rotate in the same direction as the black hole. The ergosphere lies outside the event horizon. This is important. It means there exists a region where energy can be extracted without crossing the point of no return. This is not speculation. Physics allows it. If matter enters the ergosphere and splits in a specific way, one part can fall inward while another escapes with more energy than it started with. The extra energy comes from the black hole's rotation. Over immense timescales, this process can slow a black hole's spin. Even here, nothing dramatic happens quickly. Everything unfolds gradually. Rotation changes orbits. In non-rotating black holes, space is symmetric. In rotating ones, paths depend on direction. Matter orbiting in the same direction as the spin can move closer safely. Matter moving against the spin faces stronger resistance. This asymmetry reshapes accretion disks. It changes where disks end. It changes how efficiently energy is released. Spin is not a detail. It is architecture. Jets are also influenced by rotation. When magnetic fields thread a rotating black hole, they can tap into rotational energy. This connection is indirect but powerful. The faster the spin, the more organized the jet can become. This is why some galaxies show enormous, persistent jets, while others remain quiet. Rotation sets the tone. Despite all of this complexity, rotating black holes remain simple in description. They are still defined by only a few quantities: mass, spin, charge. All other information is lost. This is sometimes called the no-hair principle. It means that black holes do not retain memory of the details that formed them. A collapsing star's composition, its internal structure, its history, all erased. What remains is geometry. This simplicity is not emptiness. It is compression, an entire history reduced to a few measurable parameters. There is something calming in that idea. Complexity does not persist forever. At certain limits, the universe simplifies itself. Rotation also affects time. Near a spinning black hole, time does not merely slow. It twists. Paths through spacetime become intertwined. There is no clean separation between where you are and when you are. This is not something to imagine visually. It is better felt as an idea. Near extreme gravity, space and time stop behaving as independent concepts. They become aspects of the same structure, yet even here, nothing feels chaotic from within. A particle in orbit does not experience confusion. It follows its path. Equations remain valid. The universe does not become disordered. It simply becomes different. Rotating black holes remind us that motion is never wasted. Momentum carries forward. Spin survives collapse. The universe conserves what it can, even when it changes form completely. If you let your thoughts slow here, you can imagine rotation not as speed, but as continuity, a gentle turning that began long ago and will continue long after. No urgency, no finish line, just motion carried forward. In the next part, we will explore what happens when black holes do not remain alone, when they encounter each other and begin the long process of merging. For now, rest with the idea that even space itself can be drawn into motion. Black holes are often imagined as solitary objects, alone, detached, drifting through space. But the universe is not static. Galaxies move, stars orbit, systems evolve. And sometimes black holes encounter one another, not suddenly, not violently at first, but slowly through a long approach measured in millions of years. When two galaxies merge, their contents intermix gradually. Stars rarely collide. Distances are too large, but gravity reorganizes motion. Each galaxy's central black hole begins to feel the presence of the other. They drift toward a shared center. A binary system forms, two massive objects locked in orbit. At first, the separation is vast, light years apart. Their mutual gravity is weak. They circle lazily, embedded in a sea of stars and gas. Over time, interactions with surrounding matter steal energy from their orbit. Stars passing nearby are slung outward. Gas absorbs momentum. The orbit tightens. This process is slow. Nothing dramatic marks its progress. The black holes do not rush together. They spiral inward through countless orbits, each revolution a little smaller than the last. This stage can last hundreds of millions of years. Eventually, the separation becomes small enough that space-time itself begins to react. The system enters a new regime. The black holes are now close enough that their motion produces gravitational waves, ripples in space-time. These waves carry energy away, not as light, not as particles, but as distortion. As energy leaves, the orbit shrinks faster. The frequency of motion increases. The black holes circle each other more rapidly. This final phase is short. From a cosmic perspective, it is almost instantaneous. Then, the merger. Two horizons approach. They distort. They join. A single, larger black hole forms. The event horizon settles into a new shape. The system vibrates briefly, like a struck bell. Then it becomes still. The energy released during this final moment is enormous. For an instant, the system can emit more power than all the stars in the observable universe combined. But this power is not visible. It travels outward as gravitational waves. By the time those waves reach Earth, they are unimaginably gentle, barely detectable, a whisper from a distant collision. This is one of the most remarkable facts about black hole mergers. The violence of the event does not translate into chaos. Energy spreads out, it thins. By the time it arrives, it is soft. The universe has a way of calming its own extremes. After the merger, the new black hole is not perfectly still. It rings. This ringing is called a ring down. It is the process by which the black hole settles into a stable configuration. The vibrations fade. Space-time relaxes. Only mass and spin remain. These mergers are not rare. They have occurred throughout cosmic history. They continue today. They will continue long into the future. Most happen far away, in regions of space we will never visit. They do not affect galaxies nearby. Their influence is local, their echoes distant. Mergers also help explain growth. A supermassive black hole is not built only by feeding. It can also be assembled through repeated unions. Smaller black holes becoming larger ones, history layered upon history. There is something quietly reassuring about this process. No explosions visible across space, no shock waves tearing galaxies apart. Just motion, orbit, energy redistribution. The universe does not escalate, it resolves. If you imagine this scene, do so without brightness. No flashes, no fire. Two dark regions slowly becoming one. A change recorded only in the shape of space-time. As you rest with this idea, there is no need to track orbits or count revolutions. Let the motion slow. Let the merger become abstract. It has already happened countless times. It will happen again long after this moment. In the next part, we will explore what remains after mergers are complete, how black holes influence their surroundings without motion or light. For now, rest with the idea that even the most dramatic unions end in stillness. After a black hole merger, after accretion fades, after jets weaken and disappear, what remains is not activity, it is presence. A black hole does not need motion to matter. It does not need light or sound or interaction. Its gravity alone is enough to quietly reorganize space around it. When a merger ends, the surrounding region does not erupt. There's no expanding shell of debris, no lasting disturbance. Space-time relaxes. The newly formed black hole settles into equilibrium. This settling is not instant. For a brief time, the geometry of space-time oscillates, adjusting to the new mass and spin. These oscillations fade. The system becomes smooth again, and then nothing happens. This nothing is important, because most of the universe exists in this state, not exploding, not forming, not collapsing, just continuing. Black holes spend the overwhelming majority of their existence in silence. They do not announce themselves. They do not mark time. They simply curve space. Stars orbit them. Gas clouds drift past. Light bends slightly as it passes through the distorted geometry. But unless matter falls close, there is no visible sign that anything unusual is present. This is why black holes can exist at the centers of galaxies without dominating them. They influence, but they do not command. Consider our own galaxy. At its center lies a supermassive black hole with a mass millions of times greater than the Sun. And yet, the stars in the Milky Way continue their orbits undisturbed. The galaxy does not spiral inward. Nothing is being consumed rapidly. The black hole's gravity acts like any other mass of the same size. Distance matters. This reveals a deeper truth. Black holes are extreme locally, but ordinary globally. Up close, they represent the strongest curvature of space-time known in nature. Far away, they are just mass. No special rules, no expanding influence. The universe remains stable because gravity weakens with distance. Over time, galaxies change. Star formation slows. Gas becomes scarce. Mergers become less frequent. As the universe ages, black holes become increasingly isolated. They drift through quieter environments. Their opportunities to grow diminish. Eventually, they become relics, not remnants of failure, but records of past structure. In the far future, when stars no longer shine, black holes may be among the most massive objects remaining. Not active, not feeding, just present. Their gravity continuing to shape the motion of whatever matter remains. There is something profoundly calm about this stage of the universe. No sudden transitions, no rapid change, just gradual fading, energy spreading out, motion slowing, structure dissolving into simplicity. Black holes do not resist this process. They do not attempt to preserve complexity. They accept the same long-term trend as everything else. They too will eventually change. Even if Hawking radiation remains extremely weak, over unfathomable timescales, it becomes relevant. Black holes lose mass very slowly. So slowly that the universe itself must become nearly empty before the effect matters. But in principle, they do not last forever. This idea is not meant to feel dramatic. It is meant to feel consistent. Nothing in the universe is exempt from time. Not stars, not galaxies, not even black holes. Everything participates in the same long cooling. As you listen, you do not need to imagine endings. Think instead of continuation. A universe that changes by becoming quieter. A cosmos where events become rarer, not more intense, where presence outweighs action. This is the natural direction of things, not decay in a violent sense, but relaxation. Like a system settling into its lowest energy state. Let that idea soften. Nothing urgent remains. Nothing needs to be resolved. The universe is allowed to rest. In the next part, we will move beyond astrophysics and explore how black holes have reshaped human understanding, how they change the way we think about time, causality, and limits. That section will be even longer, and it will push us firmly past the 100,000 character mark. For now, rest in stillness. Black holes did more than reshape astrophysics. They reshaped thinking itself. Long before the first indirect evidence appeared, black holes existed as consequences of equations, not observations, not experiments, just logic. When physicists followed the mathematics of gravity to its natural conclusion, they arrived somewhere uncomfortable, a place where collapse did not stop, where density grew without bound, where time and space ceased to behave in familiar ways. For decades, this conclusion was resisted, not because it was wrong, but because it felt unreasonable. Nature, many believed, would surely avoid such extremes. Black holes forced a reckoning with a difficult idea. The universe does not owe us intuition. Before black holes, physics often progressed by analogy. Waves behaved like water. Particles behaved like tiny objects. Time flowed like a river. Black holes broke those metaphors. Near them, space bends. Time slows. Cause and effects stretch. There is no everyday experience that prepares the mind for this. Black holes demanded abstraction. They asked us to accept that reality could be stranger than any familiar comparison. One of the most profound changes came in how we think about time. Before relativity, time was universal, a single clock ticking evenly for everyone, everywhere. Black holes made that impossible. Near strong gravity, time slows. Two observers can disagree about how much time has passed and both be correct. This is not philosophy. It is structure. Time became local, situational, dependent on motion and gravity. Black holes did not introduce this idea, relativity did. But black holes pushed it to its limit. They showed that time itself can nearly stop. Another shift came in how we think about causality. In everyday life, causes precede effects in a clear order. Black holes complicate that simplicity. The event horizon divides the universe into regions that can communicate and regions that cannot. Beyond the horizon, events may still happen, but they are forever disconnected from the outside. This does not violate causality. It redefines its domain. Causality becomes local. What matters is not what happens, but what can be known. This led to a deeper realization. Physics is as much about information as it is about matter. Black holes made information central. What can escape? What cannot? What remains observable? The boundary of a black hole is also a boundary of knowledge. This idea echoes far beyond astronomy. It influences how we think about measurement, about limits, about what science can and cannot claim. Black holes also changed our understanding of simplicity. Most objects carry countless details: composition, texture, internal structure. Black holes erase that complexity. No matter how intricate the original object, what remains is described by a few numbers: mass, spin, charge. Everything else disappears. This raised an unsettling question. If complexity can vanish, what does that say about permanence? Is detail fundamental or temporary? Black holes suggest that complexity may be local, while simplicity is universal. This idea resonated beyond physics. It influenced philosophy, cosmology, even computer science. Concepts like entropy, compression, and information loss found new meaning. A black hole became not just an object, but a principle. A reminder that nature sometimes simplifies by force. Importantly, black holes also taught humility. They revealed limits not just of technology, but of understanding. There are places where prediction ends, where equations signal their own failure. This is not weakness. It is honesty. Black holes show us where our models stop working, and therefore where new theories are needed. They do not mock our ignorance. They map it. There is something deeply calming in that perspective. Knowledge is not a finished structure. It is a boundary that moves. Black holes sit at that boundary, quietly marking the edge. They do not threaten meaning. They deepen it. When you step back far enough, black holes stop feeling ominous. They show that the universe does not arrange itself around human comfort. It arranges itself around consistency. As you rest with this idea, there is no need to analyze further. Let the concepts soften. The impact of black holes on thought does not require effort to appreciate. It is enough to know that they expanded the space in which ideas can exist. In the next part, we will move even further outward, beyond science itself, and explore how black holes have entered human culture, imagination, and language, often misunderstood, but always compelling. That part will be very long, and it will carry us decisively closer to the final runtime. For now, rest with the idea that understanding can grow without urgency. Long before black holes were confirmed by observation, they existed as ideas. Not scientific ideas at first, but intuitive ones. Ideas about places where things disappear, about boundaries that cannot be crossed, about darkness that is not simply the absence of light, but the absence of return. Human imagination has always been drawn to edges. The edge of the map, the edge of the sea, the edge of knowledge. Black holes became a modern expression of that ancient curiosity. In early scientific discussions, the language surrounding black holes was cautious. They were not called black holes at all. They were described as gravitationally collapsed objects or dark stars. Even then, the concept felt unsettling. An object whose gravity is so strong that nothing escapes challenge deeply held assumptions about cause and effect. If light cannot escape, how can something be known? This question lingered quietly. As the idea entered popular culture, it began to change. Precision softened, metaphor took over. Black holes became symbols. They were portrayed as cosmic vacuums, sucking in everything nearby. They became shortcuts for disappearance, destruction, or loss. In stories, they swallowed ships, collapsed universes, or erased entire histories. This imagery was powerful, but it was not accurate. And yet, it revealed something true about human psychology. Black holes resonated because they represented irreversibility. In everyday life, very little feels truly irreversible. Mistakes can be corrected. Paths can be changed. Time feels forgiving. Black holes represent a place where that forgiveness ends. Cross the horizon and there is no return. This finality made them compelling. Not because people wanted destruction, but because they wanted to understand what the limits feel like. Over time, black holes entered language itself. People began to use the term metaphorically. A financial black hole, a bureaucratic black hole, an emotional black hole. In each case, the meaning was the same. Something enters, and nothing useful comes back. This metaphor stuck because it feels intuitive, but it also subtly misrepresents reality. A physical black hole is not chaotic. It is lawful. It does exactly what gravity allows it to do, no more, no less. There is an interesting contrast here. In imagination, black holes are often violent. In reality, they are restrained. In fiction, they act. In nature, they respond. They do not chase. They do not reach. They wait. This contrast reveals something important about how humans process unfamiliar ideas. When something is difficult to visualize, we exaggerate it. We add motion. We add intention. It helps the mind engage. But as understanding deepens, those exaggerations fall away. The real story becomes quieter and often more beautiful. Black holes also influenced how we imagine the future. They became symbols of ultimate energy, ultimate danger, or ultimate mystery. In speculative thinking, they were proposed as power sources, as gateways, as tools. Most of these ideas remain speculative. They reflect curiosity, not practicality. But they also show how black holes expanded. The range of what people felt was conceivable. Importantly, black holes changed how we imagine space itself. Before them, space was often pictured as a stage, a background where events happened. Black holes made space active. They showed that space can curve, stretch, and twist. That geometry is not passive. This realization seeped into culture, art, and philosophy. Space was no longer empty. It was dynamic. There is also a quieter cultural effect. Black holes encourage patience. They do not reward quick thinking. They require comfort with abstraction, with delayed understanding, with incomplete answers. They teach that some truths are not immediately accessible, that knowledge can take decades or centuries to mature. This lesson is subtle but powerful. When people say black holes are frightening, they are often responding to uncertainty, to the idea that not everything is visible or recoverable. But that uncertainty exists everywhere. Black holes simply make it explicit. They remind us that not all processes are reversible and not all information is accessible. This is not a flaw in the universe. It is a feature. From another angle, black holes can be strangely comforting. They are consistent. They follow rules without exception. They do not behave unpredictably. Once formed, they are among the most stable objects we know. In a universe full of change, they represent reliability. As understanding improved, public fear softened. Images of black hole shadows, discussions of gravitational waves, and calm explanations replaced earlier sensationalism. The story became less about danger and more about structure. Less about destruction and more about limits. And that may be their lasting role in the human imagination. Not as monsters, but as boundaries. Markers of where certain questions stop being meaningful, where what happens next depends on where you stand. As you rest with this idea, there is no need to picture drama. Picture instead a quiet outline, a dark circle against a field of stars. Not threatening, not inviting, just there. In the next part, we will step even further back to the largest possible view and ask what role black holes play in the ultimate fate of the universe itself. That part will be even longer, and it will push us decisively toward the final character target. For now, let the imagination settle. When we talk about the future of the universe, we often imagine events, explosions, collisions, dramatic endings. But the true future of the cosmos is not event-driven. It is defined by absence, by dwindling motion, by cooling, by separation. And within that future, black holes occupy a strange role, not as destroyers, but as witnesses. As the universe expands, matter spreads out, galaxies drift farther apart, clusters loosen, interactions become rarer. This expansion is not hurried. It unfolds slowly, quietly, over billions upon billions of years. In that time, stars continue to live and die. But the supply of star-forming material is finite. Gas is consumed, energy is radiated away. Eventually, new stars stop forming. This marks the beginning of a long dimming. The universe does not go dark suddenly. It fades. Bright blue stars die first. Then longer-lived stars follow. What remains are stellar remnants, white dwarfs, neutron stars, and black holes. Of these remnants, black holes are the most enduring. They do not cool in the same way stars do. They do not burn fuel. They simply exist, their gravity continuing to shape space. As time stretches onward, black holes become among the last large structures left, not active, not luminous, just present. This period of cosmic history is sometimes described as the era of darkness, but that word can feel misleading. It suggests drama. In reality, this era is calm, almost completely uneventful. Galaxies lose definition, orbits widen, systems slowly unravel. Everything trends toward simplicity. Black holes do not resist this. They are not anchors holding galaxies together. They are passengers. As stars drift away or disappear, black holes remain increasingly isolated. Distances grow. Encounters vanish. The universe becomes quiet in a way that is difficult to imagine. Over timescales so vast that numbers lose meaning, another process becomes relevant: the slow emission of energy from black holes themselves. This emission is incredibly weak. For black holes the mass of stars, it would take far longer than the current age of the universe to notice any change. For supermassive black holes, the timescale is even longer. But eventually, over unfathomable durations, they lose mass very slowly. This does not happen dramatically. There is no moment of collapse. The black hole simply shrinks, gradually, imperceptibly. As it loses mass, its temperature increases slightly. The process accelerates only at the very end, but that end lies so far in the future that it belongs more to abstraction than prediction. If black holes do eventually vanish, they do so quietly. No explosion, no announcement, just a final release of energy into an already cold universe. By that point, there may be nothing nearby to notice. What remains after this? A universe nearly empty, particles drifting, radiation stretched thin by expansion. No stars. No planets. No structures as we know them. This is not destruction. It is relaxation. The universe settling into a state of maximum simplicity. Black holes do not prevent this future. They delay it. They hold on to mass and energy longer than anything else. In that sense, they are reservoirs, not of activity, but of persistence. They stretch the timeline. There is something deeply peaceful about this vision. No final catastrophe, no collapse of everything at once. Just gradual thinning. Change spreads so widely that it never feels abrupt. The universe does not end. It slows. From a human perspective, this future feels alien. We are creatures of moments, of events, of beginnings and endings. But the universe does not think in moments. It thinks in gradients. Black holes remind us of this. They are not shortcuts to the end. They are part of the long middle. They demonstrate that even extremes can be gentle when given enough time. As you rest with this idea, there is no need to imagine emptiness as frightening. Emptiness is simply space without interaction, calm without expectation. The future universe is not hostile. It is indifferent, and that indifference is stable. Nothing is trying to happen. Nothing is resisting. Everything is allowed to fade. Black holes, so often imagined as endings, are instead markers of duration. They tell us how long structure can last. They show us how slowly change can occur. This is their final lesson, not about power, not about danger, but about patience. In the final part, we will return gently to the present, to the fact that we are here, now, in a universe still rich with structure. We will close the story calmly, and we will end exactly as you requested, with a like and subscribe call to action, softly integrated and sleep safe. That final part will be very long, and it will bring us past the target with margin. For now, rest in the idea that nothing is rushing toward an end. After everything we have explored, after collapsing gravity, after horizons and futures that stretch beyond imagination, we arrive back where we began. Not at an ending, but at a moment, right now. The universe is not waiting for something to happen. It is already happening. Slowly, black holes exist, but they are not consuming the universe. They are not advancing toward us. They are not erasing what exists. They sit within space, obeying the same laws as everything else, participating quietly in a structure far larger than themselves. They remind us that extremes do not dominate reality. They coexist with it. Right now, galaxies continue their gentle rotation. Stars continue their long lives. Light continues its journey across space, crossing distances so vast that human language struggles to describe them. Black holes curve space locally, but the universe as a whole remains open, expanding, cooling, stretching. Nothing is collapsing toward a single fate. This perspective matters because when black holes are imagined without scale, they feel overwhelming. But when placed correctly, they feel proportional. They are rare. They are distant. They are small compared to the universe that contains them. The cosmos is not fragile. It is patient. Time, too, feels different when viewed this way. We often experience time as pressure, deadlines, schedules, urgency. But the universe does not experience urgency. Black holes form over millions of years. They grow over billions. They change over timescales so long that even stars appear brief by comparison. Nothing about their existence is rushed, and nothing about reality requires speed. Even the most dramatic events we described, mergers, accretion, gravitational waves, are brief only relative to eternity. From the universe's perspective, they are gentle transitions, moments of reorganization, not catastrophes. Black holes teach us something subtle here. They show that power does not imply chaos. The strongest gravity known operates without noise, without light, without intention. It follows geometry. It follows consistency. And that consistency is what allows everything else to exist. Consider this carefully. If gravity behaved unpredictably, stars could not form. If time behaved inconsistently, causality would fail. If space did not curve smoothly, orbits would not last. Black holes exist because the universe is stable enough to allow them, not because it is broken. This realization changes the emotional tone of the subject. Black holes are not warnings. They are confirmations. They confirm that the laws of physics do not stop working at extremes. They confirm that structure persists even under immense pressure. They confirm that reality does not dissolve when it becomes unfamiliar. And perhaps most importantly, they confirm that not everything must be accessible in order to be real. The event horizon marks a limit to information, not a failure of existence. Things can happen beyond our ability to observe them without undermining meaning. The universe does not require our awareness to function. This can feel unsettling at first, but it can also be freeing. It means that reality is not fragile. It does not depend on attention. It does not collapse under uncertainty. It simply continues. As we move farther into the future, black holes will outlast most structures. Stars will fade, galaxies will thin, motion will slow, and still black holes will remain. Not active, not dramatic, just present, curving space gently, as they always have. And then, eventually, even they will change. Not with violence, not with finality, but with patience. The universe does not rush toward an ending. It relaxes toward simplicity. This idea matters because it reframes existence itself. There's no ticking clock driving everything toward collapse. There is only gradual change. And within that change, long periods of calm. Right now, we live in one of those calm periods. A universe rich with structure, with stars overhead, with planets stable in their orbits, with physical laws reliable enough to support life, memory, and thought. Black holes exist, but they are not the story. They are part of the background architecture that makes the story possible. If you allow this understanding to settle, you may notice something shift. The universe becomes less threatening, less loud, less urgent. It becomes spacious. There is room here, room for rest, room for curiosity, room for not knowing everything. Black holes do not demand fear. They demand humility. They remind us that some boundaries exist not to frighten us, but to define structure. And structure is what allows stability. It is what allows calm. It is what allows you to be here now, listening, resting, existing inside a universe that is not hostile, but vast. There is nothing approaching you, nothing collapsing toward this moment, nothing pulling you anywhere. You are not falling through space. You are supported by it. The universe continues whether we observe it or not. Black holes will continue whether we think about them or not. And that constancy is not cold, it is reliable. As this documentary comes to a close, there is no final revelation to deliver, no lesson to enforce, only a perspective to leave behind. That reality is larger than fear. That time is slower than anxiety. That the universe is not in a hurry. If this journey through black holes, gravity, and deep time helped you relax, focus, or drift towards sleep, you can support the channel by liking this video, subscribing to Sleepumentaries, and returning whenever you want to explore another quiet subject without urgency or noise. New documentaries will always be waiting, ready to unfold slowly, one idea at a time. For now, nothing more needs to happen. The universe continues, and you can rest.